Welcome to another Phi Guy Francois production. Today we're going to be talking about refraction and Snell's law. He's going to make that mistake there. We are not talking about smell, but we are talking about light and waves. So let's get into a practice problem which refers to this. So the problem that we're going to be talking about is a beam of light enters from air n equals 1.000, we'll get to that in a second, entering water n of 1.333 with an angle of 60 degrees from normal. What is the angle of the refracted beam? So let's take a look at the values that are given to us, because it's always important to list out your known values. So this one here, this n value, that is the index of refraction. Now, index of refraction is different for every material, so you have to see that it's in the air here. So when we write it down, we say it as n of air, or the index of refraction of air. The other one that we are mentioning here is the water's index of refraction, 1.333. And the last thing is 60 degrees from the normal. Okay, now we may be asking what angle is this? So you have to read this with where it's talking about. It says that it is the 60 degrees from the normal when it's talking about the beam of light entering the water. So this is the angle that's coming in at, not what it is in, not what it's leaving with, not what it's transmitted with. So we have our angle of incidence being 60 degrees. So now let's get into Snell's law, because this is where we're heading given these values. So Snell's law noted that if you have a ray coming in, the angle that it comes in at relative to this normal line, so that's relative to a perpendicular between the two substances, would come in with one angle and leave with another. And what he noticed was that if you gave each substance a set value known as an index of refraction, it has to follow this equation, this index of refraction for the initial side times the sine of our angle of incidence equals the index of refraction for our transmitted side times the sine of the angle that is transmitted. So where does this index of refraction come from? Well, later on it was discovered that the indexes of refraction actually relate to the speed of light within the substance. So the index of refraction is equal to the speed of light in a vacuum, which is given at 2.99 times 10 to the 8th meters per second, divided by the speed of light in the material. So this is actually very crucial to our understanding of the universe, and that speed of light actually changes when you enter different substances, much like how well you can move in regular air versus if I forced you to, say, slog through molasses. You might have a much more difficult time. The same could also be said as a metaphor for how it occurs with light. Because of this change of speed, we end up with a change of angle. There's a much more complicated process to it, but this is as far as our understanding needs. So we have our equation here. This is our general equation. Now let's set it up as our specific to our problem. Specifically to our problem, we have our angle incidence side is the air side, because we're coming in from the air, entering into the water. So everything that is incidence is air, everything that is transmitted is water. Now that we have those in, we can actually throw in our values. So we have 1.000 times sine of 60 equals 1.3333 times sine of the angle that will exit into the water. That is our unknown. That is the thing that we're trying to solve for. So once we have this, we can move the 1.333 onto the other side. Since it is a constant multiplier, we can move it onto the other side through division. So when we move that over, we're left with sine of the angle in water. Now, to get rid of sine is not like getting rid of a constant multiplier like how we did here. What we have left to us is sine is a function. It is something that we do to something else. It's not something that stands by itself. Okay, so it's similar in the way that you would treat a square. If you were to try to get rid of a square, you couldn't multiply or divide the square away. What you would have to use is the inverse function, which happens to be the square root. In sine's case, its inverse function is known as inverse sine or arcsine, and it is denoted by the representation of sine to the negative 1. That doesn't mean it's actually being raised to the negative first power. That's just how it looks because they didn't really have a better way of denoting it. Sometimes you will even say it, instead of showing sine to negative 1, it will actually say arcsine, A-R-C-S-I-N. So we take the arcsine of all of this, whatever is on the inside here. As you may know, I don't like to resolve values until we have completely solved for the variable in question, which we now have. So we can actually calculate this out, and when we plug everything into there, and making sure that our calculator is indeed in degree mode, that's very important, we end up with an angle that is 40.52. Now we have to put this back into context because all of our problems always have to deal with the context of it. So when we put this back into context, we find that the refracted beam has an angle of 40.52 degrees from the normal. It's always from this normal line. So there you have it, a very simple, straightforward solve for an angle-to-angle equation using Snell's law. I hope this was helpful to you, and I will see you next time on Phi Guy's Fabulous Adventures.